Welcome, everyone, to the Fibre Channel Industry Association's presentation of the versatility of Fibre Channel, multi-protocol magic. My name is Howard Johnson, and during today's presentation, we will be covering the topic of the Fibre Channel data transport mechanism. Just a few words about the Fibre Channel Industry Association. It's a mutual benefit, nonprofit, international organization of manufacturers, system integrators, developers, vendors, industry professionals, and end users. And the FCIA is our host for today's webcast. Today's speakers are myself, Howard Johnson. I'm a technology architect at Broadcom. I'm also the Insights Fibre Channel Technical Committee Chair. Joining me today are Ed Mazurek, a principal engineer at Cisco. He is also Insights Fibre Channel expert group member, and Dave Peterson, a principal engineer at Broadcom and the Insights Fibre Channel international representative.
Hello, everybody.
Howdy, y'all. Just a little note about the Fibre Channel Industry Association before we get started. This is our 30th anniversary year, and we've been really excited about the prospects of the Fibre Channel marketplace. In 2025, we are at the point where we have over $50 billion of Fibre Channel revenue. Over 35 million ports are still in service, with over 160 million ports having been shipped. So quite an impact that the Fibre Channel industry has had on the marketplace, and it still remains one of the strongest enterprise technologies in the market. During today's presentation, we're going to start with Ed, who will give us a summary of the Fibre Channel protocol, give us a brief description of how the transport works, and then he'll break down how the Fibre Channel building blocks form the Fibre Channel data transport. At that point, I'll take over and we'll delve deeply into the data transport mechanism. And through the examples of several upper layer protocols, we'll see how Fibre Channel is quite versatile. And with that, I'll turn it over to Ed.
Okay. Hi, everyone. Thanks, Howard. I appreciate it. I'll be talking about a short summary of Fibre Channel. And we'll start out with Fibre Channel is 30 plus years old. The FCIA itself is celebrating its 30th year, but Fibre Channel itself is a little bit older than that. And it was purpose built, starting design back in the late 80s, I believe. And it's a high speed, low latency networking technology for primarily connecting servers or hosts to shared storage or storage arrays. Before that, if a server wanted access to storage, that storage would be local in the server itself. But Fibre Channel opened that all up and allowed network access to storage so that storage could be shared across multiple servers. The primary use is enterprise storage area networks, which are one or more switches interconnected with varying numbers of servers and storage arrays connected to them. It's really specifically designed for very reliable block level data transfer in databases and in the storage area or storage array data stores, otherwise known as LUNs or namespaces, whatever the name is for the type that they're in. It currently does work on SCSI, FICON, which is for mainframe, NVMe and RDMA. It carries commands and data efficiently for those transports, and there's some others as well. It's high performance. The current spec is 128 gigabits, and since links can be aggregated, the sky is kind of the limit here. It provides lossless in-order data delivery across a topology that's an arbitrary Fibre Channel switch topology, and it's has very robust and high availability features, which is one of the things that's made it great. It it's a typical server is connected to 2 fabrics for redundancy and resiliency. There are multiple host bus adapters, which is like the Fibre Channel NIC. There is multipathing drivers that specifically are trained to handle errors and switch back and forth if there are problems detected. In the storage area network switches themselves, they have multiple links. They have various levels of error correction, buffer-to-buffer credit, resiliency, dual supervisor switches on the high-end directors, all sorts of different features to ensure that there is a very, very high availability for the servers and the storage in these networks. We talk a little bit more about performance. So it started out at 1 gigabit, and it's now currently 128 gigabits, with 256 being currently designed. Links can be aggregated, as I mentioned, and but so you can achieve even higher than the 128 gigabits currently. And individual servers themselves can have multiple links and stuff, so you can have huge amounts of bandwidth available in these SANs. The SAN itself ensures rapid data transfer, critical application databases, server virtualization kind of things. It's very low latency, and it's lossless, as I already mentioned. It uses a very efficient credit-based flow control mechanism, such that the credits that are flowing back and forth are actually not taking any of the bandwidth that the data itself could possibly use. So that's quite a feat in a networking protocol. If you compare that to other protocols, like with priority flow control and Ethernet, the priority flow control pause frames themselves take up network bandwidth. You compare that to buffer-to-buffer flow control, and they really don't. We kind of fit the credits in between the packets and the frames as they're going on the line, not taking up any bandwidth. It does prevent network congestion, and when there is congestion, it does handle it well. And with that network congestion mechanism, we're not trying to drop any frames unless the situation is very dire. So the built-in reliability and availability, there's automatic failover to other fabrics. There's lots of redundancy built in between multiple modules and multiple links, and the encodings on the individual links, and the credit recovery mechanisms, and all sorts of things that allow minor errors to be recovered transparently where you probably won't even know they're occurring. And sometimes things are a little, in my side of the woods, when I'm dealing with customer problems and that kind of thing, sometimes we see lots of different problems under the covers, and the customer never even realized that they were going on. And all this is just allows a continuous operation of the SAN. We have SANs that have been up for years and years and years with virtually no problems at all. And they do scale. It's not just a small number of servers and a small number of storage arrays. They can support a large switch fabric, which is basically a network of interconnected switches with inter-switch links. So, and the topology can be whatever topology you would like. We have, single switch topology. We have edge core. We have edge core edge. We have full mesh. We have all sorts of things. And some of our customers are very creative in their topologies. I'll say that. But yeah, but it can handle it. No matter what topology you put in play. And the last bullet on the slide is it does use zoning to isolate traffic and secure data paths. Zoning is a mechanism that allows predefined grouping of devices, so that only those predefined and pre-authorized groups of devices are allowed to communicate. And this is all programmed into hardware, such that there cannot be any devices communicating that have not been pre-authorized. So zoning is a large part of the success of Fibre Channel. It does ensure that even though SAM with many devices in it, only the administrator is the one that's really calling the shots and only deciding who is allowed to communicate with who. If we look at the stack here a little bit, it's a little different than the OSI stack, but you'll see some common things in here. We have FC0, the physical layer, which is like the physical media and cabling and set connectors and such. We have FC1, which are really the encodings. It shows here 8-bit, 10-bit, well, that's fairly old, around the 8 gigabit speed time, but now we're up to 64, 66, or even higher as we go into faster speeds. FC2, the signaling protocol, it defines the frame formats and the flow control, like buffer-to-buffer flow control, and the basic communication rules like link initialization, all that kind of thing. Up to FC3, common services. There's lots of things included in here, such that like the name server and the management server and the zoning server and all these things here that allow the fabric to operate as one and provide the information that the individual devices need to find each other and communicate each other automatically. And FC4 is the upper layer protocol. That's what ULP means, the upper layer protocol mapping layer. And there's one of these for each of the upper layer protocols to allow these upper layer protocols that are listed access into the Fibre Channel SAN. So you see there's FICON, there's SCSI, there's NVMe, there's IP even, RDMA, and there's some others as well. So all of these protocols have their own little individual mapping layer that then provides access into the Fibre Channel stack itself. Okay, so let's talk about a little bit about how I/O works in the very simple examples here. So we have lots of terms. Why, I always say, why have one term when we can have 10 terms for something? And in this case, the typical term is initiator and target. And that really is a good term to do, because initiator is the side, which is typically the server. It's the one that's going to initiate the I/O in either direction. But we could also call it requester, transmitter. It could be sender, it could be host, could be server. On the mainframe side, it could be channel. And the target has other names as well: responder, receiver, etc., all the way down to control unit for the mainframe. So these things kind of change sometimes. Some of the meanings sort of change depending upon who's sending and who's receiving. But there's always an I/O initiated, and that would be from the server. And if we look here for an example of a write operation, we'll see that the host, well, we're not seeing it. Okay, the host is going to initiate an I/O. In this case, it's 8K in size, and that I/O is going to make its way from the initiator, the server, over to the storage array, otherwise known as a target. Now, once the target gets this, he actually can take a look at this I/O, decide see how big it is, and decide how much space he has. He can clear space, he can get ready for the I/O. Once he's done, he sends what's known as a transfer ready in back to the initiator. And when the initiator gets that, he starts sending the data in one after another. And since we allow 2K payload in each of our frames, he'll end up sending 4 frames of data, making up the 8K that he originally wanted to write. And once the target gets it and tucks it safely away somewhere, he will respond with a status message indicating that it was a good I/O operation. The write complete goes back to the host, and at that point in time, that is complete. So that's a write operation. It's a little bit more complicated than what you'll see in a minute, which is the read operation. If we look here at the read operation, I guess the order is a little messed up, but we see here the read command, which is just a small frame, goes from the initiator to the target. And the target at that point in time just starts sending data back This is silly. Okay, I'll just go to the end. It starts sending data back again. Since it's an 8K read, he's going to send back 4 2K frames of data and then immediately send back a status message indicating that the read is complete. And at that point in time, the host has all of its all the data that was requested from the target. It's a very simple operation. Now the target, doesn't have to send all 4 of these in one shot. He can like interleave IO to other hosts that are sending to it because the target's handling multiple IOs concurrently. But in this example here, he's just sending the 4 frames and then sending the status message indicating that the read is complete. And when the host gets that, he knows all the data is there. It's a very simple read operation. And I'll let you know that reads and writes can be very large. The data length field is 4 bytes, and so it can be megabytes in size if needed. That's not your typical IO operation, but it's a possibility given the flexibility here of the protocol. Okay. So now if we just go into a little deeper, what do the building blocks look like? So we have here, if you look over on the right first, you'll see that we have different exchanges across there. So an exchange is basically an IO operation. And IO I'm using loosely because some of these aren't transferring really any data necessarily. But initially, when a device wants to join the fabric, he's going to do a fabric login. And that is otherwise known as a floggy. And pretty much everyone in the Fibre Channel SAN world has heard of floggy. So floggy is a fabric login. And that actually goes into the fabric and obtains what I call a layer 3 address, an endport ID. Some call it an FCID, but this is the routable ID for that device that just logged in. Now the target will have to do that as well. He'll have to do a floggy as well. Once that happens, typically the server will query the name server and log into that and query the name server and figure out who he's allowed to talk to based upon the zoning. And then he'll send the next thing over, which is an endport login, which is another exchange. And this is basically logging in from the server to the target itself. And once that's done, the data transfer protocols can occur. And there could be multiple of these going concurrently. And as you can see by the crossing arrows and stuff, these IO operations can sort of overlap as they get down onto the wire and stuff. But they're all maintained independently and individually, such that when all of the frames and the status messages for the individual IO completes, that IO operation is done. So you can see that underneath each of these it says exchange, and that exchange means it's the complete IO operation, and that comprises of one or more sequences flowing between the originator and the responder of that. And a sequence then itself is one or more frames, and then the frames contain the Fibre Channel header, and it contains the information, the payload to be transferred. That may or may not be actual SCSI or NVMe or other data, and it just might be control data going between on the fabric login between it and the switch, or in the endport login between the initiator and the target, or it can be a host of other commands and extended link services things as well. Lots of stuff can happen there in that payload. And this is just another way, a little bit more information on it. So the upper layer protocol has these information units, and these are mapped, to each of the upper level protocols. And these information units are mapped to these sequences. You can see they're going from IU1 to sequence 1. And then the sequences are what are transported in Fibre Channel frames, and they're one or more frames. So this is just, and all this is, you can see the purple outside. This is all wrapped up in an exchange itself. An exchange is a complete IO operation that ends with a status indicating that it was successful or perhaps not. And one final frame before I hand it over to Howard. This is what flows on the wire, the frame, the fiber channel frame. You can see it starts with the starter frame indicator, and there's several of those indicating what's in that frame. There's an end of frame at the end indicating the frame is done. Extended headers, I don't want to talk about too much, but there is a frame header in each one of these. And the frame header has multiple different fields inside of it that we're not going to get into too much. Howard will get into a little of them. But you can see that the DID and the SID, those are the end port IDs, otherwise known as the addresses, that were received by the host and the target during the flogging process. And there's other things in here that are really indicating what sequence you're in, and are you starting a sequence, or are you transferring the sequence? All sorts of control information, such that you can know a lot about what's happening on the wire just by looking at the frame header. And right before the EOF, there is a CRC value, a 4-byte CRC value that will allow this entire frame to be error checked. And if it's bad, it will be thrown away, discarded as a invalid CRC error. But regardless of whether it's a good CRC or bad CRC, we still detected it as a frame, and the buffer-to-buffer flow control mechanism will take over. So at this point, I will hand it over to Howard, and he'll talk about some transport mechanisms. Thanks, everyone.
Thank you very much, Ed. And I really appreciate the background on Fibre Channel. Now let's take a little bit deeper dive into that frame header, because this is the mechanism that's going to be used by the FCP transport engine, if you will. And we're going to look first inside the frame header at the R control field. That R control field tells us the type of the frame, if you will, and what it's going to be used for. For the most part, you can see here on the left-hand side of the slide that the R control field is divided into two subfields. There's a routing field that indicates really the function of the frame, whether it's for device data or extended link services or basic link services or some type of other link control. That's specified in the routing field. For our purposes today, we're going to focus on the device data frame type. So the routing field will be set to 0. When it's set to 0, then the information field of the R control indicates what the frame is going to be used for. So whether it's a solicited data frame or an unsolicited command frame is indicated in the information field. And the key thing about this is that it's very generic in its descriptions here, so that this mechanism can be used by any of the upper layer protocols. The second half of the FCP transport feeds off of the type field in the frame header. Initially, FCP, which stands for Fibre Channel Protocol, was designed in conjunction to support SCSI. However, what we found is that the basic data movement operations are relatively generic, and therefore the type field for the FCP transport has been made generic, so it's not just for use by SCSI anymore. Essentially, the host bus adapters have optimized their implementations so that the hardware and firmware provides an assist and acceleration for the FCP data transport type. Other ULPs, such as FICON, noted here as the FCSB, which stands for single byte, and what we're looking at here is the transport mode, which happens to be also known as high performance FICON. There's also NVMe and RDMA as upper layer protocols that have taken advantage of this capability. By setting the type to 8, this is where that triggers the hardware and the firmware engines to be able to drive the data data movement operations into hardware so that they're quite fast. These types are then reused for things like commands, the transfer ready, the data movement itself, and the response. So effectively, the very basic operations in a transport are all collected together in the FCP transport type. Those then are mapped to the hardware assist or the fast path inside the data engine in the HBAs that are attached at both ends of the wire. So they're able to move data very quickly on and off the wire. What we're going to look at here is a comparison between those upper layer protocols. Typically, what we see are the upper layer protocols listed across the top, and then down on the left-hand side, we see the information field categorization for the device data information categories. The most common are the unsolicited commands, which are just command operations for each one of the upper layer protocols. Then the data descriptor, which is the indication that on a write operation that the target is ready. So it's going to say, hey, I've got all the memory allocated to receive your data. So I'm going to send you the transfer ready to say, go ahead and send it over. Then the third one is the solicited data, this is the workhorse, which is transmitting all of the data across the wire and managed by that fast path data engine, if you will. And then command and command status and solicited control, those are the response and confirmation frames that are used by each one of the upper layer protocols. You can also see that the high performance FICON also uses the unsolicited control and the unsolicited data types for various types of FICON controller status indications. And then NVMe and RDMA use the extended command status to deal with particular error type indications when communicating those back and forth. So those just are examples of some of the efficiencies that are leveraged by the upper layer protocols that are part of the standard fiber channel FC2 layer mechanisms. So now let's take a look at each one of these individually, and we can see how they map and are utilized by the data transfer engines. As mentioned before, SCSI was the first upper layer protocol that used the fiber channel transport mechanism. SCSI has an initiator and target mechanism. It's often referred to as kind of a client-server type of operation, where the server or initiator is the client and the server is the target. Effectively, the client is saying, hey, I just need this information, basically data, whether it's reads or writes, to send to or read from the target. The initiator will start the operation, and the target will provide the processing and response for those commands. The storage or the data itself is defined by a logical unit, which is managed by the target device. And that relates to a particular data store or volume that the target has available to it. Many of you probably refer to the storage as a LUN. A LUN is a logical unit number, which is an identifier that specifies specifically which data store or volume that we want to access. All of this information is encoded inside of the CDB of the upper layer protocol. So now let's take a look at then how this is mapped from SCSI to the FCP transport. So the SCSI I/O operations are a single exchange, and the exchange has typically three phases. The exchange begins when a command is sent from the initiator to the target to indicate that it wants to do something, whether it's a read or a write operation. The command descriptor block provides the upper layer protocol information about how to handle the data that's being transmitted. And certainly there's the identification, which is the LUN, and various flags that describe what to do with the data when we get it. The second phase of operation is the exchange of data, whether it's a write or a read operation. The initiator is going to send the frames, and the target's going to, for write operations, and the target's going to send frames for the read operation. And then finally, the exchange is closed via a status operation, where the target indicates that, hey, we've completed what we needed to do, and everything is A-OK. Now let's take a look at what the frame header looks like when we're processing a SCSI transfer. So the first thing that we'll notice is that the The type field is set to 08. And this is the mechanism that the data engine uses. So the hardware assist says, okay, this is type 8. I can map this directly to my hardware for just moving data either onto or off of the wire. So typically what's been done is that some type of a scatter gather list has been provided to be able to pull the data out of memory and put it onto the wire. And this is all managed by the HBA hardware. And he uses that type field of 08 to know that he can do that. The second space that we're looking at is actually the data field of the fiber channel frame, but this is also the ULP header. So for SCSI, I mean, this is our SCSI header space. So the first thing that we see is the LUN, which indicates what chunk of storage that we want to access. And then the command descriptor block provides information on what we want to do with that. There's also an additional command descriptor block area in case we have additional actions that need to take place. And then finally, a data link that tells us how much data follows in the rest of the data field associated with the SCSI operation. Now, as we jump into another example, the FC-SB6, which is the Fibre Channel single byte revision 6, is the FICON specification. FICON is a mainframe architecture, probably known to many of you either as S390 or IBM Z. And FICON's been known to run over several transports, whether it's been parallel channels or serial channels. When it was called SCON at that time, and now over Fibre Channel. So we refer to the protocol as FICON. Supports a number of different operating systems, such as ZOS or ZVM, TPF or Z-Linux, and various other operating systems as well. The data in a mainframe is extended account key data formatted, which is variable sized blocks. And then the command sets are associated to be able to read those variable sized blocks for whether the device is a tape, a printer, or DASD or storage. Connections are logical path based. So that means there's a logical connection that's established between the application and the end device. And that establishment is managed by the channel or the initiator and the controller or the target. On the storage side, there's a logical control unit that manages the storage, and each of the logical control units can support up to 256 devices. So these are roughly equivalent to what SCSI LUNs would look like. And then finally, FICON has the ability to provide explicit acknowledgments. So it leverages Fibre Channel's Class 2 explicit acknowledgement mechanism or passive acknowledgments. So Class 3, think of that as like just a simple data frame or datagram, if you will. So FICON was one of the first protocols then to map itself onto the FC transport. There are actually two modes that FICON uses. There's a command mode where we're just leveraging the transport mechanisms as is, and the commands are sent in separate IUs. What this means is that each IO operation is executed as separate exchanges, and they're often referred to exchange pairs. That was the initial implementation or adaptation of FICON onto the FCP transport. Later on, transport mode was invented to improve upon the efficiency, and it exploits that hardware engine that we've been talking about for the SCSI functions. So it mimics an FCP command IU, and therefore the operations are contained within a single exchange. As mentioned in SCSI, FICON also uses a command descriptor block that describes the operation. However, what we'll see here next is exactly the pieces that we need for the FCP transport engine to be able to leverage the accelerators. So the first thing that we see is that the type field is 08. That indicates that this is an FCP transport frame, and it can be managed as such. So now the data engine in the HBA hardware is engaged. And then what we'll notice kind of immediately is in what used to be the LUN area, really is a target device. We have a special value. It's FE is the first byte of that field. That's another trigger for the hardware to know what to do with the data that's coming in. And in order to be able to leverage that capability, the SCSI architectural model was modified and allocated that tag to the Fibre Channel single byte or FICON architecture space. So now the engine knows specifically that this is a frame that is being used for FICON data. There are a few other fields in the command descriptor block that are also used to trigger specific things on the target side or the control unit side. But for the most part, the data engine is really just looking at the first two pieces, the type field and then that first byte in the target device area. Similarly, as we move on to an NVMe example, so currently the Fibre Channel NVMe is at release 3. It's a highly efficient protocol. It's certainly defined for parallel operations over a Fibre Channel infrastructure. It is also one of the mechanisms that's taking advantage of the high performance capability of Fibre Channel and the low latency aspects of it for flash systems. So NVMe was really designed to take advantage of the flash capabilities, and it's a parallel protocol that can be used over the Fibre Channel infrastructure. The NVMe operations are very similar to what we've discussed for both SCSI and for FICON. Single operation is contained within an exchange, and we have the same 3 phases. We have the command phase, which has the NVMe command descriptor block. So very similar to the SCSI CDB in that it includes a connection identifier, a sequence, and a data length, which we'll see here shortly. The data operation, which is the phase 2, is also very much the same. Host sending data or the subsystem sending data, depending on whether it's a write or a read. And then, of course, finally, there's the status operation that marks the end of the exchange. If for any reason that there's a recovery operation that needs to be executed, an error response is provided, indicating that either the transporter or the data or a data transfer error occurred. This is actually beneficial in the Fibre Channel space because we have something that is known as sequence level error recovery, which is a faster recovery mechanism than what was typically defined for NVMe over fabrics. So this provides us with just kind of a lower level recovery operation without having to have the upper layer protocol manage the recovery. So we can handle this at the, I'll call it the sequence layer, if you will, for NVMe. As we take a look at how NVMe maps, what we see here is exactly what we saw in SCSI, that the type field is set to 8. Again, this triggers the HBA hardware to say, okay, I can use my FastPath engine. And then we look at the target device space, and what we see first is a new byte that's now referred to as the format ID field. And this one is Foxdog. And again, the SCSI architecture model was expanded, and they allocated Foxdog for use by Fibre Channel. The next piece that we'll notice is that there is an FC ID. What this is the Fibre Channel upper layer protocol identifier. So for NVMe, that identifier is 28. Now we have some additional information that can be used and leveraged by the FastPath engine in order to process the NVMe commands much more efficiently. The ULP header is shown here in green, and what we see is we have the connection identifier that tells us where we're going, and a sequence number that tells us where we are in our operation, and of course the data length. Then there's some additional space, additional CDB operations. So there's a submission queue entry that's identified there, a few other flags. And then below this will be the actual NVMe data that's going to be utilized. And then our final example is RDMA. So the FC-RDMA specification has been something that we've been working on for a couple of years now. The specification is reaching completion. We're in the request for comment phase, and we're expecting to go to letter ballot fairly soon. which means it'll become a public document probably within the next 4 to 6 months. In the case of RDMA, the adapting it to Fibre Channel was quite straightforward. RDMA certainly has a request to responder relationship for being able to access memory on other devices. So one server could access the memory on another server as if it was its own memory. It uses the hardware capabilities that are available within the system to offload the CPU from dealing with the memory access operations. It also allows us a method for being able to take information that is coming off of the wire or from memory onto the wire without having to copy it into a holding buffer, if you will, for that transfer. This provides us with ultra low latency, very high throughput, and no load on the CPU. The way the RDMA uses the Fibre Channel transport is exactly the same way that NVMe uses the Fibre Channel transport. Operations are done within an exchange. It has the same 3 phases. The command phase, we have an RDMA command descriptor block. We're kind of starting to see a pattern here with regard to the reuse characteristics of that fast path data engine. The data space, the requester sends frames, the responder sends frames depending on whether it's a write or a read. And then we have a status operation that indicates when the operation is complete. Again, similar to NVMe, if there's any type of an error that occurs, we can utilize an error response to indicate that a data transfer error has occurred, and we can recover from that. Once again, taking a look at how that maps onto the Fibre Channel frame itself. Again, the type field is set to 08, indicating, hey, this is a Fibre Channel transport frame. We can use the data engine, and in our ULP header, that first byte is set to Foxdog, indicating that it's an Insights Fibre Channel upper layer protocol adaptation. The only difference here is that the FCID is 29, indicating that this is an RDMA frame. The rest of the header is RDMA unique. It has the command sequence number there, data link there, and there's also a base transport header that is included in this space. Below the ULP header is the data itself. And that wraps up the exploitation by the upper layer protocols. Before I move on, however, I'd like to point out that one of the very, very early adaptations of Fibre Channel included the adaptation of avionics. So many of the military jets that are using Fibre Channel are still using that today. So, for example, the F-35 is using Fibre Channel inside for communication within the machine. A lot of these have been adapted as mil specs, and we've listed them here for your reference. Just wanted to point it out that this is one of the very early adaptations of Fibre Channel into a very unique industry. So let's wrap this up. What we've seen is that FCP was originally built for SCSI, but we've transformed that FCP engine to support multiple protocols. We now support FICON, NVMe, RDMA, Avionics, and IP. The SCSI architectural model was also adapted to take advantage of the hardware assist capabilities that are built into the HBAs. So we generalized the FCP data transport from being just SCSI unique to being Fibre Channel transport generic. And we're exploiting the Fibre Channel frame characteristics, specifically the R control and type fields, as triggers to be able to utilize the hardware engines. The HBA designs themselves have been adapted to put much of the data movement operations into hardware and provide a little bit of firmware to assist those operations. So this is really the magic behind the Fibre Channel data transport engine. During our conversation today, we got a summary of Fibre Channel as a high-performance, low-latency transport protocol. It's lossless, reliable, and secure. We also had Ed tell us a little bit more about how the transport works, how the send and receive operations, reads and writes, and initiator and target relationships are established. Ed also described the various building blocks of Fibre Channel, the exchanges, sequence, and frames that are common to all of these upper layer protocols. We then delved into the transport mechanism itself, seeing how the R control and type fields are leveraged to help the data transport engine move data quickly. And then finally, we took a look at the multi upper layer protocol examples. We looked at SCSI, FICON, NVMe, RDMA, and then we just had a note there on avionics. So at this point, we've concluded the presentation and we'll open it up to questions. Dave, I believe we have a few questions to go over.
Yeah, we do. Yeah, good job, Ed and Howard. Good stuff. Big fan of Fibre Channel. So yeah, we got a few questions here. I think we'll just kind of, some of them are categorized in the same item or area. So we'll go from the top here. The first one, are you sure that data type FICON for FICON and NVMe is 08 hex? According to FS6 standard, there are 18 B and 1C for FICON and 28 hex for NVMe. That is correct. But the important thing that we're trying to put across here is the reuse of the FCP data engine, which is 08. And all other control type traffic, you know, that I categorize in data and control, basically in Fibre Channel, those will use those data type codes that you mentioned for FICON in those specifically. But for data transfers, it's going to be 08. Then Howard mentioned there's the command mode versus transport mode. So it's a transport mode FICON that uses 08 for the data operations.
Yeah, that was a very insightful question. I think the key thing to understand there is that these upper layer protocols are using different types depending upon the operation itself. For data movement, they're using type 08 to be able to take advantage of that data transport engine that's been implemented in hardware.
All right. So yeah, if there's any further questions on that, please let us know. Another one before we have some interest in the RDMA realm is the 256 gig option expected to be over a single pair of fiber optic cables. So I believe yes. Howard.
Yes, that is correct.
256
gig is a single lane specification, same as 128 gig.
Okay, and yeah, we're actively working on the PI9 spec. So the next ones we kick off in the AI RDMA realm. So what is the future of Fibre Channel for object store, mainly used by AI applications? But then as people kind of hit on in the next few questions, yeah, allowing up-to-date RDMA protocol implementation is, you know, that was basically why we did the FC-RDMA. So if somebody so chooses to implement that, you can do it over Fibre Channel. What is missing is the stuff kind of above. In particular, there's some people, looks like they're on the Linux Windows side, that are there Linux or Windows drivers available to support our FC-RDMA? So at this time, no, I'm not aware of any. But that's kind of the chicken and the egg issue. But the capability is there. Go ahead, Howard.
Yeah, I was just going to comment that the Fibre Channel Industries works very closely with the operating system vendors. And when we come out with a new standard such as FC-RDMA, we'll then begin working with those vendors to provide drivers to be able to support the standard. This is common. Most recently, some of our activity around the fabric notifications involve similar type of cooperation between the Fibre Channel industry and the operating system vendors. So our expectation is that that is the second phase, although it's kind of outside the scope of the Fibre Channel standard itself. Having the RDMA standard available makes it much easier to have those conversations and start work on those pieces. To get back to the question about accessing of object stores, this is kind of a common question, and it's still to be determined as to how the artificial intelligence industry is going to impact Fibre Channel. The way I like to characterize it is that many of the enterprise customers, their intellectual property is in their data that they have. And if they want to be able to leverage the capabilities of artificial intelligence, that data will have to get exposed to those engines. So how that happens is yet to be determined, but it's certainly something that the Fibre Channel industry is watching very closely and wanting to continue to provide low latency solutions for the possible exploitation by the artificial intelligence industry.
Yeah, there's quite a bit of data out there in the FC realm that can be used for AI's models and blah, blah, blah. All right, so yeah, one note, I don't know if we got touched on, it looks like our write operation got a little messed up in the slides, and we'll have to fix that up, but should mention, for a write operation, we do have the capability to disable the first transfer ready, which effectively allows you to send a first burst of data. And, for a lot of RDMA type applications, they're just not sending a huge amounts of data, boom, it'll be very, very quick. And that's all using the FCP engine. So just a note, and I guess the last question, got a bit here. FC can be used to feed data to AI models, particularly when utilizing FC or NVMe-FC as AI networks require very attributes that the Fibre Channel was engineered for. Example, low latency, lossless transmission, reliability, and robust congestion control. FC-RDMA could enhance the speed of data delivery to AI models. Do you see an opportunity for FC-RDMA to be leveraged for this purpose, and perhaps even for AI internode communications by utilizing the dedicated FC networks that customers are having deployed? So yeah, that's kind of what Howard was talking about and stuff. We have the capability. Standard is there. Howard, Ed, do you have anything more in that realm?
Yeah, I see this as this is an emerging area for the Fibre Channel industry. This was largely the reason that we wanted to have the FC-RDMA standard in place, which is why we took it upon ourselves to go ahead and develop the standard and get that out into the marketplace, so that we can kind of get ahead of this curve a little bit. As everyone knows, the AI world is moving extremely fast. So we hope to see a lot more activity in this space going forward as we provide access for those AI engines to, as I mentioned before, the intellectual property that Fibre Channel customers have encoded in their data.
Right. All right. So we got another one here. We got a couple minutes left. So in today's world versus 30 years ago, who was developing state diagrams and state machines for the industry when a protocol implementation is defined? The T11 committee or the FCIA? That would be the T11 committee, particularly .2. Howard can expand on that if you want.
Yeah, exactly. So the relationship between the Fibre Channel Technical Committee, also known as T11, and FCIA is harmonious. That is, the FCIA looks outward into the marketplace and gathers information about where the market is heading, and then provides that back to the T11 Technical Committee. But the Technical Committee itself is what's responsible for defining all of it, whether it's a state diagram, state machines, protocol specifications, and the like. That's all done by the Fibre Channel Technical Committee.
All right, I think that is it on the questions.
All righty. That's the last of the questions. After this webcast, please let us know. We value your feedback. Give us some ideas on how to improve our presentations. We will post the Q&A answers in a blog as well. If you'd also like to follow us at FCIA News on Twitter to learn about future webcasts, and then we also have several webcasts on demand that several of which you can see listed here on the slide. And finally, thank you all very much for your time and your questions. We really appreciate you guys taking time out of your day to join us. And thank you all, and have a great rest of your week.